All right, so this week we're in section 3.5. This is the very last section in chapter 3, and we're talking about optimization. Optimization is an application of pretty much everything we have done in chapter 3, and you can kind of look at it as where all of chapter 3 has been leading up until this point. Now, this is calculus for business and economics, and so we focus on those specific applications, business and economics applications. But if you were to take our Math 400 course, our full Calculus 1 course, we would be spending a whole lot more time in this section. And the reason for that is because there's a huge amount of variety in the types of problems we could do, which would be classified as optimization problems. However, because this class has a little bit more narrow of a focus, this section will actually not be terribly long for us. We're going to talk about the process of optimization. I'm going to run you through 3 examples, and then we're going to be done. So just bear in mind that this is a major part of what we use differential calculus for, is optimization. And if this section feels brief, don't let that be misleading. In the broader scheme of things, this is a very large subject, optimization. So let's go ahead and get into it. I want to talk through the process for solving optimization problems, and then we're going to work through some examples. So when you're faced with an optimization problem, what you're doing is you're being asked to either maximize or minimize something. So in a business and economics sort of setting, that oftentimes might look like maximizing profit. That's something a business would want to do. Or minimizing production costs. That's another thing that we might want to do. So problems are always going to involve either maximizing or minimizing something. But it's going to be presented as a word problem. So in most cases, you're not going to be given a function right off the bat. Our first example, we will, but you're going to see shortly after that usually you have to come up with the function yourself that you want to optimize. And that's kind of step 1 here. So step 1 of this process is translating a word problem into mathematical form. And there's some bullet points here. I'm not going to read through these word for word, but essentially you have to decide what do the variables represent in your function that you're optimizing. In some examples, it makes sense to draw a picture. You will see that in one of the examples that we do, 1 or 2 of the examples actually. And then you have to identify constraints. So constraints are going to be what help us to reduce our function down to just one variable, as you're going to see in the examples that we do. So once you've kind of identified all of this stuff, you should end up with what we call an objective function. There might be more than one function or equation that show up in your work, but there should only be one function that you're going to get your maximum or minimum value from. And that's typically what we call an objective function. So you use the description of the problem to determine what your objective function should be. An example would be if I'm trying to maximize profit, then I should have a profit function, which I would then find a maximum value for. And step 2 also talks about that constraint that I had mentioned as well. If there's more than one variable, as there oftentimes will be in your objective function, we use this thing called a constraint to create substitutions in that objective function, which reduces it down to a function of one variable. So you'll see that'll make a little bit more sense when we do an example that involves that step. Step 3, you don't always need to do this, but oftentimes you're going to want to identify the interval on which your objective function needs to be optimized. So there might be a restriction on the domain of your function. A good example would be, like a revenue function, which depends on X, the number of units that you sell. X could not be negative even if the function that you're defining your revenue function in terms of just by itself is defined everywhere. Those functions are oftentimes polynomials, Polynomials have a domain of all real numbers, but in the context of that problem where the inputs represent something literal, something physical like units sold, it doesn't make sense to use negative values for x. So you have to think about the context of your problem and if that puts any restrictions on your domain in the form of an interval. So steps 1 through 3 are kind of all setup steps. We start doing the math, or more specifically the calculus, here in step 4. You'll notice it's a really big step here. So we have talked through in chapter 3 about how to find relative and absolute extrema. So that's where you're going to get your maximum and your minimum values from. Step 4, basically, to summarize all of this, is to use those techniques that we have talked about. So finding critical numbers, and using the closed interval method, and identifying maximum and minimum values using your first or second derivative tests. All of these things that we have done to find max and min values are used here. And then finally, step 5 is kind of a check. So you reread the problem to be sure that you're answering what the original question asked for. Part of step 5 also is knowing what units to assign to your answer, because these are word problems, and most of the time you're going to need some sort of units attached to your answer. So, as I had mentioned before, we have 3 examples we're going to run through. Let's start with this one. The revenue function for Starbright sneakers is given by r of x equals 208x minus 0.2x squared dollars, where x is the number of pairs of sneakers sold. How many pairs of sneakers must the company sell to maximize its revenue? Okay, so now we detailed a very long process on the previous page, and I'm not going to go through number steps like step 1 from that process. Let's do that here, then step 2, and write that. I'm going to kind of walk through it, just pulling out the parts that we need. So from that process, we need an objective function, and the objective function, you can determine what it should represent by reading the end of the problem. We want to maximize revenue. So I need a function that represents revenue. This problem gives me that function right at the beginning. So this is one of the less common examples where the objective function is told to you in the description of the problem. More often than not, you're going to have to come up with that yourself. But to start us off easier, we have our objective function right here. Now what are we trying to do? I'm trying to maximize or minimize this thing. Specifically, I'm trying to maximize it because that's what the problem's asking me to do. And that makes sense. That's what a company would want to do. They want to maximize their revenue. So to determine a maximum value, we have some methods that we talked about throughout chapter 3. There's the closed interval method, which is a way of finding absolute extrema. And that method is not available to us because for this function, the interval from 0 to infinity is the interval that we can consider to be the domain for this function. In fact, if we want to be a little bit more picky about it, even this is technically not accurate because, again, this interval contains numbers like 2.8 or 3.56701, things that are not whole numbers. But this function in particular, it doesn't make sense for x to be anything but a whole number because it represents something discrete. It represents numbers of pairs of sneakers that have been sold. You can't sell 2.8 pairs of sneakers. But for simplicity, we'll go ahead and consider this interval to be our domain. And basically, we don't want to use any negative numbers, so that's why we specified this. This is not a closed interval, so I can't use the closed interval method for finding absolute extrema in order to solve this problem. That's okay. It basically just means that if we're going to get any maximum or minimum values, they're going to come from relative or local maximum or minimum values. And that's where we would use either our first or second derivative tests. So first thing I want to do is again, steps 1 through 3 were all about setting up your objective function, finding constraints. All of that's given to us. So we're jumping all the way to the calculus step here. We want to start by finding the derivative of this thing, r prime. R prime of x is equal to 208 minus, this would be 0.4x. Okay, the purpose of finding the first derivative is to get critical numbers. This is defined everywhere, so we won't get any places where the function is not differentiable. So instead, we find critical numbers by setting it equal to 0. This is easy to solve. Takes 2 steps, right? Add this term over, divide both sides by 0.4. So 208 divided by 0.4, that comes out to 520. That's the only critical number that we got, okay? Now, at this point, you might look at that and just think, okay, we've solved it. We have to sell 520 pairs of sneakers to maximize revenue. And you would technically be correct. However, we have not done the steps to verify whether this gives us a maximum or a minimum value. So that's where we want to go a little bit further and tell which of those two it is. So there's 2 options that we have available to us. We can either use our first derivative test or our second derivative test. To me, because this is a polynomial, I think the second derivative test is actually the easiest approach, because the second derivative is very easy to find. It's 0.4. Okay, it's a constant function. Notice this is negative for all values of x, so surely negative for 520 when I plug that in. Remember, if you have a critical number where the function's second derivative is negative, then that implies that we have a relative maximum or a local maximum at that value. And again, the reason why, in case you forgot, is because a negative second derivative tells me that my function is concave down. And concave down usually will imply a maximum at kind of that highest point there. So we can say that by the second derivative test, revenue is maximized when 520 pairs of sneakers are sold. I'll just say pairs are sold. Okay? So you notice I gave a justification here. The work for that justification is just a couple of steps here. This was, again, a simple example. And then so after my justification, I kind of stated we maximized revenue after selling 520 pairs of shoes or pairs of sneakers. So there has to be units attached to the answer that you're given. You can't just write 520 and circle it and call it a day. Like this is an application problem. You need to kind of give a little bit more than just that. But let's take a look at a slightly harder example. Notice here there's no function that's given to us. We have to come up with one ourselves. So in this example, it says Brian has 800 feet of fencing to build a pen for his hogs. If he has a river on his property that he can use for one side of the pen, what is the maximum area of the pen? So in this problem, he has a fixed amount of fencing to work with. And we know that he wants to build a rectangular, actually, does it say that? It doesn't actually say that, but it is. I know that it is implied for this problem, so I'm going to write that in. He has 800 feet of fencing to build a, let's say, rectangular pen for his hogs. That's actually very important that we have that written in here, because if we don't assume that the pen is rectangular, then there's not really enough information to solve this problem. We need to know a little bit about the shape of the pen so that we can get an area formula for it. But this is an example involving geometry, which we don't see very much of in this class because, again, we're focusing on business and economics applications. Geometry doesn't show up that often in these applications, but it shows up all over the place in a full calculus class. And here's one area where it kind of leaks into the stuff that we're talking about. So this is an example where it really, really helps to draw a picture. We're told that there's this river on his property, right? So this is like the river. There's some ripples in the water, so you can tell that it's a river. And what we want to do is we want to build a rectangular fence on this property where we really only need to use the fencing for 3 sides of that fence, because the 4th side is the river. we don't need to put a fence along that river. That's what's being implied here anyways. So thinking about what I want here, I know first of all how much fencing I have available to me in order to build this thing. It's a total of 800 feet. And in addition to that, I'm going to have to label some of these sides with some variables so I can start using them in computations. Let's say that the width of this thing is x, and the length of it, I'm going to call it y. Okay, notice that because it's rectangular, if that's an x, then this would also have to be x. They have to have the same length, otherwise it's not a rectangle. So from this, my first sentence implies a constraint. And remember, a constraint is something that restricts your problem in such a way that reduces your objective function down to one with only a single variable in it. So what I'm going to do is represent this first sentence in terms of the variables that I have here. I have a total of 800 feet of fencing, and I've labeled the 3 sides that I'm using all 800 feet of fencing to build. So if I add all of these up, I have x showing up twice. I'm going to call that 2x plus the y. That should equal 800. Okay, so this is a description mathematically of that first sentence. Next thing I want to do, and I'm going to manipulate this. I'm going to change the way this looks in just a minute, but it's not obvious why I would want to do that yet. So let's leave that there for now. I want to set up an objective function. So to find an objective function, we're looking for the thing that we are trying to maximize. It says here that we are trying to maximize the area of the pen. And this is where it's important that we know that it's rectangular, because a rectangle has a very simple area formula. I'm going to call it A for area. A is equal to length times width, or x times y. Okay? This is the thing that I'm trying to maximize. Now, as it's written, I can't do anything with it yet because it's got 2 variables in it, and this is a single variable calculus class. We don't know what to do with multivariable functions, which is a thing, and that isn't a major objective study in math, and calculus in particular, but not here. We don't have access to that yet. So what I'm going to do is come down to my constraint, and I'm going to say, from this, I know that x and y are related to each other, and I want to use that relationship to change this into a function with only one variable. The simplest way to do that is to solve this for y. Y is equal to 800 minus 2x. What that does for me is it creates a substitution for the y in this function so that everything will now be in terms of x. I can now call it a of x, area in terms of just that x right there. It's equal to xy, but y is equal to this, 800 minus 2x, which I can distribute that x in and call it 800x minus 2x squared. Okay, so that's critical. That's something that we needed in order to solve this problem. Okay, now could I find a closed interval on which this is defined? Well, no, I can't. However, there is a restriction on it. If it's not going to be super useful for solving this problem, but we can still say what it is. Because this function is defined in terms of x, I want to find a restriction on x specifically. X cannot be as small as 0, but it can be as close to 0 as we want to make it. For practical purposes, you would not make x microscopically small. But for, just to consider all possibilities, we can bring x as close to 0 as we want without actually making it equal to 0. And basically what that would be like is shrinking this and this edge of our fence down to a very, very teeny tiny quantity, right? Making this a very long rectangle, because the smaller x is, the larger y will be, because we're still using a total of 800 feet of fencing. X can also be as big, or almost as big as 400. Now, where did that 400 come from? Well, remember, we have 800 feet of fencing, and whatever I use for the side here, I have to use the same amount of that here. So if I use 400 feet of fencing for x, I'm going to use another 400 feet here. That adds up to 800 feet. I can't use all of my fencing for both of these x's, because then I would have none left for y, and I wouldn't have a rectangle anymore. but I can get as close to 400 as I want because it'll still leave a little bit left over for y. Now this is an open interval. It's not a closed interval, so I can't use my closed interval method. That means I'm going to solve this problem in essentially the same way that I solved the last problem. Find your critical numbers. A prime would be equal to 800 minus 4x. That's defined everywhere, so we can only find critical numbers where that's equal to 0. This one is very easy to solve. X would have to equal 200 in this case, okay? Because again, solve that for x, it takes 2 very straightforward steps to do that. Even though we only got one critical number, we don't want to just jump to the conclusion that that's where our maximum occurs. It is where our maximum occurs, but you need some kind of justification for that. So once again, the second derivative test is going to be the way to go. Find the second derivative of this. It's equal to negative 400. As we saw before, this second derivative is negative everywhere, so it's definitely negative when x is equal to 200. We have a concave down part of our curve when we are at our critical number. That implies that we have a relative maximum. So once again, I can say by the second derivative test, this time it's area that we're maximizing, so I can say area is maximized. Now, again, let's read the question really carefully before we finish writing this sentence. If he has a river on his property that he can use for one side of the pen, what is the maximum area of the pen? So it's not asking for the dimensions of the rectangle. If it were, then I'd be using x equals 200 for x, and then y would have to be 400, because again, we could plug 200 in for the x here to get the y. And I'd say something like is maximized when the fence is 200 feet by 400 feet or something like that. It's not asking for that. It's asking for the actual area itself. So what I need to do, since I have now determined that my maximum value occurs at 200, I have to plug 200 into the original area formula, which is either one of these. So that's equal to 800 times 200 minus 2 times 200 squared. Or if you wanted to, another approach, you could very easily, like we did, find that y is equal to 400. And we know that the area was equal to length times width anyway, so 200 times 400 will give me the same thing. But whichever approach you take, this is going to come out to 80,000. So I can say by the second derivative test, the area is maximized at 80,000 square feet. Remember, area is measured in square feet, okay? Now, it may not immediately feel like this is a business or economics problem, but the way that it kind of fits in is that we have a fixed amount of materials to use, and we want to use those materials in an optimal way. So no matter how you set up this fence, you only have 800 feet of fencing to use. However, depending on how you arrange it, you get different areas. And so it makes sense to want to make the most out of what you have. That is something that occurs in economics and business applications also. You want to maximize your output, maybe with a fixed amount of labor hours or something like that. So it kind of fits into that vein. I'm going to stop this video here. We'll do our last example in part 2.